Have you ever stopped to think that the whole idea of machines doing things for us isn't really new?
Not at all.
I mean, brilliant minds like Archimedes, Heron of Alexandria, they were already dreaming up amazing concepts centuries ago.
Yeah, Heron especially with his almost magical mechanisms. Those are fascinating early hints of that drive for automation.
Exactly. And what's so interesting is how these early ideas show this really deep human desire, to copy movement, maybe free up our time and effort from certain jobs.
It's like the seed for robotics was planted thousands of years ago.
Absolutely. So to really explore this history, today we're diving into two main sources. First, there's a comprehensive document, Origin, Evolution, and Future of Robotics, UPV, by Martin Mulatto from the Institute of Automatics and Industrial Informatics at the Universitat Politecnica de Valencia.
That's a mouthful, the A2 Institute.
It is. And second, we'll take a look at some ideas from the article, Ethics and Artificial Intelligence, Need or Urgency.
Right. So our mission today, for you listening, is to give you a clear picture of how robotics has evolved, from those ancient roots right up to the potential future directions we're seeing now.
And we won't forget the kind of questions that pop up with AI becoming more involved.
Crucial point.
Definitely. So we'll start by digging up those historical precedents, then look at the birth and boom of industrial robots.
Then mobile robots, humanoid ones.
And finally, wrap up with some thoughts on future trends and those ethical questions.
Yeah.
Okay, let's get into it, starting way back with those early inventions.
Okay, so if we go way back to Archimedes' time, that's like 287 to 212 BC, we already see fundamental mechanical bits being figured out. Levers, springs, pulleys, the Archimedes screw.
Basic stuff, maybe,
Yeah.
but totally essential for building more complex machines later on.
Absolutely foundational. Then fast forward to the 1st century BC, you've got Heron of Alexandria doing the things you mentioned earlier.
Yeah, those birds that seem to fly and drink on their own, and those mechanisms that must have just seemed like magic back then.
And even a primitive kind of jet propulsion, imagine seeing that.
Wild.
But what's really striking about Heron is that he wasn't just creating illusions, he was applying physics and mechanics to get automated movement. It's a very early example of engineering focused on making automata. Sets a really interesting precedent.
Then we jump forward quite a bit, several centuries, to the Middle Ages. We start seeing animated automata powered by clockwork technology, like the famous Strasbourg rooster.
Ah, yes. Clockwork was key there. The precision of those mechanisms allowed for more elaborate, lifelike movements for these figures.
So progress in one area, clockmaking,
Yeah.
directly fueled these more sophisticated automatic devices.
Exactly. That rooster moving at set times was a real engineering marvel for its day.
And we can't skip Leonardo da Vinci during the Renaissance. Around 1499, he designed an animated lion,
Amazing.
plus key inventions like the centrifugal pump and belt transmission. The man was a visionary in so many fields, including the sort of early robotics.
Da Vinci's vision was just incredible, so far ahead of his time. That lion, even if it wasn't fully built, represents that search for, giving artificial creations natural movement.
And his other mechanical ideas laid groundwork for later automation, too.
Definitely.
Okay, moving on to the 18th century. We have Vaucanson's famous mechanical duck in 1738. This thing could flap its wings, simulate eating, even, excretion.
Right. It was incredibly elaborate for the time. It caused a huge stir because it seemed so realistic. The complexity inside was impressive.
Pure entertainment, sure, but also showed what engineering could do in terms of mimicking biological processes.
A powerful demonstration.
Okay, and one last key point before we hit industrial robotics proper. The UPV source mentions the Jacquard loom from 1801.
Ah, yes. This is crucial.
Because here we see a program basically stored on punch cards controlling the weaving process. That's a clear hint of programmable automation.
Exactly. The Jacquard loom is a turning point. It introduces that idea of programming into automation. The punched cards were instructions for the machine telling it what pattern to weave.
A direct ancestor of the computer programming used in robots later on.
Precisely. So what this all shows is that long before the word robot even existed, people were already imagining and building machines to automate tasks. That drive was there.
Which brings us right to where things really start to accelerate. Let's explore the origin and evolution of industrial robotics based on that UPV document.
Yeah, the timeline they lay out is pretty clear. In the 1940s, you get telemanipulators. These were devices allowing remote control of mechanisms.
Super useful for dangerous environments, right? Where you couldn't have sent a person.
Exactly. Then the 50s brought key developments from George Devol. His work really laid the foundation for the industrial robots we know.
Duvall's patents and ideas were crucial for those first programmable repetitive task robots.
He's widely seen as a pioneer. Then the 60s are pivotal. You have Joseph Engelberger and his company, Unimation.
Often called the father of industrial robotics.
Right. And their collaboration with General Motors was huge. This is where we see robotics being applied practically on a large scale in the auto industry.
That partnership really proved the potential for robots to boost efficiency and quality in manufacturing.
A game changer. Then, in the 70s, the Robot Institute of America, the RIA, is formed. And important robots like Owsley and Puma are introduced.
So the field starts to get more defined, more professional.
Yeah, the RIA formation was a milestone. And robots like Owsley and Puma represented big steps forward in capability and the range of industrial jobs they could tackle.
And from the 80s onwards, it's just widespread industrial adoption. Robots become essential tools across so many sectors.
The 80s saw a real explosion, from cars to electronics, even food production. The tech got more accessible, and the benefits of automation became undeniable for businesses.
The document gives a sense of the market size back in 2009, $0.4 trillion worldwide. And if you add software, peripherals, engineering, it jumps to $1.8 trillion. That's a seriously impressive number.
It really highlights the huge economic impact industrial robotics already had by then, a massive market that's only grown since.
And get this stat, 1.3 million operational robots worldwide in 2009, according to the World Robotics Report that year.
1.3 million, that's an incredible number of machines working globally.
It really underlines the scale of robots in the industrial workforce worldwide, a huge automated production capacity.
Definitely.
The document also has this really insightful graph showing 3 phases in industrial robot evolution. Phase 1, the start in the 60s, Phase 2, growth in the 70s, and Phase 3, industry from the 80s onwards.
And you can clearly see that growth curve just shoot up exponentially in Phase 3.
Yeah, it illustrates perfectly how industrial robotics went from being this emerging experimental tech to a fundamental, indispensable tool in modern production.
That industry phase really reflects its maturity and mass adoption.
And just to picture modern industrial robots, we have examples from big names like ABB, FA&UC. They show just how versatile these machines are now across tons of fields.
Yeah, it's not just welding car bodies anymore, is it?
Not at all.
Yeah.
You see them assembling tiny electronic parts, handling delicate materials, even doing high-precision painting.
Today's industrial robots are incredibly sophisticated. Their precision, speed, adaptability, it's amazing. Their versatility is why they're used in practically every industry imaginable now.
It's fascinating how we went from those early automatons to these complex machines driving modern production.
Absolutely.
So from the controlled factory floor, let's take a leap into the wider world with mobile robotics. The UPV document points to Robot Shaky from 1970 as an early milestone here.
Shaky. Considered one of the very first mobile robots with some level of autonomy. Its abilities were pretty limited compared to today's standards, of course.
Sure.
But it was the first demonstration that you could build a machine that could move around and make basic decisions about its environment. A huge step.
Then we see the evolution of mobile robots in industry. Started with rail-guided ones.
Then wire-guided.
And finally, autonomous guided vehicles, AGVs. The document mentions examples from companies like ACME and AGVP.
Right. That progression shows the push for more flexibility and autonomy in industrial settings. AGVs don't need fixed tracks or wires, so they're super versatile in warehouses and factories.
And outside of industry, we've got mobile robots moving into our homes, like robot vacuums. The iRoomba from iRobot is probably the most famous.
And robotic lawnmowers, like Husqvarna's Automower.
These tend to have simpler mechanics and sensors, relatively speaking.
Yeah, things like ultrasonic infrared sensors.
But they can navigate autonomously to do specific jobs.
These home robots are a great example of how the tech has gotten cheaper and more accessible for everyday tasks. Their relative simplicity works fine for what they need to do.
And we even have robots exploring space, like the Sojourner rover NASA sent to Mars.
Incredible. A robot driving around on another planet, analyzing things.
The Sojourner mission was a stunning technological achievement. It showed the massive potential for robots in exploring remote, hostile places. Really opened the door for more ambitious space missions later on.
It's clear that mobility has been this constant goal in robotics evolution, letting machines operate in more and more diverse and challenging environments.
Okay, and now we get to the fascination with humanoid robots. The UPV document touches on that long-standing human desire for a robot helper around the house. maybe one we can interact with more naturally.
Yeah, the idea of a human-shaped robot assistant, it's been a staple in science fiction, but also a serious research goal in engineering for a long time. It reflects that desire to create artificial companions that can interact with the world kind of like we do.
The document lays out a really interesting timeline for humanoid robot development. Wabot 1, back in 1973.
Then WOM in 84.
Honda's ongoing work starting in 86 and again in 2000. There's an external link provided for more on that.
Honda's work, especially with Asimo, is iconic.
Then HE5 in 92, HP2 in 95, the famous Asimo in 2000, HRP2 in 2002, Wabian in 2005, HRP4 in 2009. It's quite a list. Shows steady progress.
That timeline really illustrates the constant advancement. These robots aren't just looking more human, they're gaining more complex functional abilities too. Each model was a significant step forward.
The document stresses how knowledge and different technologies have become increasingly integrated. You see the evolution from the skeletal P1 model to much slicker ones like Asimo P2, P3.
It's impressive. You see how layers of complexity, hardware and software were added over time.
Yeah, the jump from P1, which was basically a simple mechanical frame, to Asimo, which could walk bipedally, even do dynamic movements. Yeah. It highlights the huge strides made in understanding human biomechanics and applying that to robot design.
Definitely.
And these humanoid robots are just incredibly complex structures. The source uses a Sony robot as an example, detailing all the sensors packed in.
It's a lot.
CCD cameras for eyes, infrared sensors for heat and proximity, pinch detection sensors for safe interaction, pressure sensors for touch, accelerometers for balance.
And all the actuators for movement. It's an engineering marvel, truly.
Integrating all those sensors and actuators, making them work together seamlessly so the robot can perceive and interact. That's a massive engineering challenge.
Huge.
So what about the future for humanoids? The UPV document talks about assistant robots, friendly-looking ones designed to provide information and help people.
Yeah, the idea there is that a more human appearance could make interaction easier, especially in customer service or maybe elder care. The friendly look aims to build trust and rapport.
It also mentions butler robots for household chores, but it flags the huge complexity involved there.
Oh, yeah.
Complicated mechanics, needing a semi-human look for interaction, really advanced 3D sensing, complex manipulation skills for various tasks, and just the difficulty of controlling it all.
It sounds like we're still a ways off from a robot that can perfectly iron our shirts, huh?
Seems like it. The butler robot is a super ambitious goal. It needs breakthroughs in so many areas: perception, planning, interaction. Getting a robot to do a wide range of chores safely and autonomously, still a major technological hurdle.
Absolutely.
The document also points to trends like coordinating movements between multiple robots and multi-arm robots, especially for industrial applications.
Right, those are big trends in industrial robotics, using multiple robots working together or single robots with several arms.
Yeah.
It's all about boosting productivity and flexibility on production lines, allows for more complex tasks and faster cycle times.
And finally, the document briefly mentions the research happening at the AI2 Institute itself, which actually provides a nice link to our second source, the article on ethics and AI.
Yeah, it's crucial to think about the implications as robotics advances, especially with AI becoming so integrated. That article, Ethics and Artificial Intelligence Need or Urgency, really pushes us to consider the responsibilities we take on when creating increasingly autonomous machines.
Machines capable of making decisions.
Exactly. The UPV source actually cites Moulage and others from 2002 talking about the ethics of interdependence and systems thinking. It mentions page 97 specifically.
Which makes you think about how these robotic and AI systems fit into our complex social fabric and how their actions can have really far-reaching consequences.
That idea of ethics of interdependence forces us to look at how AI and robot actions affect other systems and society as a whole. We really need a systems thinking approach to grasp the potential long-term effects and make sure development aligns with the common good.
Okay, so let's recap quickly. We've gone from Heron's clever devices all the way to today's sophisticated industrial, mobile, and humanoid robots. It's been a fascinating journey, driven by human ingenuity and that desire to automate.
And the future promises even more advanced robots with greater capabilities.
But as we just touched on, it also raises significant questions we need to tackle carefully.
It's essential, as robotics and AI keep accelerating, that we really dedicate time and thought to the social, economic, and, yes, the ethical sides of things.
The history of robotics is one of constant innovation, isn't it?
It really is, and it's kind of our collective responsibility now to guide its future in a way that benefits everyone.
So to wrap up, here's something for you, the listener, to think about. With these rapid advances in robotics and AI, what are the biggest societal shifts we should expect? And maybe more importantly, how can we ensure these powerful technologies are developed and used responsibly for the good of humanity?
Definitely a lot to chew on there. It's a fascinating world where engineering, AI, and philosophy are all converging to shape what comes next. We encourage you to keep exploring it.